Well, hello and welcome to Doc Onco's physics lessons. My name is Keith Onco, and today what we're going to be doing is we're going to be discussing electric current and Ohm's law. You know, we all use electricity and electric circuits and electric current every day of our lives. In fact, if you look at some of the pictures up at the on the screen here, we see electric cars. Whoops, let me switch that to pencil mode there. We have electric cars now where you can just plug them into a charging station and they charge up. We've had cars like Priuses and the Volt for some time now, electric cars and hybrid cars. We've been turning light bulbs on all of our lives. Now we have different types of light bulbs, but they still work on the concept of electric current, electrons flow. I think we're all very comfortable and familiar with our cell phones. Cell phones need to be charged up, and how do we do that? We plug them into a wall, electric current flows, right, and our cell phones are charged up. In the morning you want to make a piece of toast, you plug your toaster in, you put the handle down, and electric current flows, and it turns your toast from regular bread into a nice crispy toast that you can put something on and eat it for breakfast. So, you know, and there are hundreds of thousands of other applications where we use electric current and in every facet of life. And so the question is, just what is electric current? Well, if we look at this picture right over here, we have a wire, a cross-section of a wire. And over on the right-hand side, we have electrons. And these electrons are just sort of randomly moving, and that's what electrons will do in a wire or most devices, or I'm sorry, most materials. They just randomly move from atom to atom to atom to atom to atom, right? Collectively taken up, their random movement comes to a zero. The vectors of their movement add up to zero. And so we don't get any real electron flow in the material. If, however, I placed a set of positive charges over here and a set of negative charges over here, what I would be doing is I would be setting up an electric field, put the positive charge a little better there, I would be setting up an electric field inside of this wire, okay? And so what do electrons tend to do when they're in an electric field? Well, they tend to go towards the positive part of that electric field. So while the electric field is going from left to right, the motion of the electrons, instead of just being random now, is going to be from right to left. They're going to want to, the electrons are negatively charged, they're going to want to be attracted to the positive charge over on the left-hand side here. And what are we going to get? We're going to get electron flow inside the wire. Well, this electron flow is known as current, electric current. Okay, so electric current is simply electron flow within some material. So what can cause the electric field inside of a wire? How can we get that? Well, one of the most common ways that we achieve that is with the battery. We're all familiar with batteries. These are a couple of AA batteries. There's AA's, AAA's, 9-volt batteries. There's all kinds of different kinds of batteries, right? And simply the way that a battery works is generally you have two electrodes inside of a battery, right? One tends to be negatively charged, one tends to be positively charged. And so if I connected a wire to these, what's going to happen? Well, the negative charges are going to move to the positive charge. Okay, they're going to have that desire, right? So there's going to be a force that's going to want to pull these negative charges to the positive terminal. Okay, what happens when they get here? Well, this acidic solution in here is an electrolyte, right? And that is going to cause the electric particles to want to come back over here, right? And they're going to be energized, and you're going to start the same cycle all over again. Okay, so that's very briefly the way a battery works. We don't have to worry about that too much. We just want to be able to apply what happens due to a battery. We have that electric field inside of a wire, okay? And so we're going to do that today. So if we come down here a little bit, we have two basic kinds of setups, right? And the one on the left is called a series setup, a series circuit. And the one on the right is called a parallel circuit. And we don't have to worry about that right now with the differences between series and parallel, but you can probably clearly see there is a big difference between the two. The one on the left, if you don't recognize that, is the common way that a flashlight is set up. Right? You generally have two batteries. Sometimes you have three batteries in the flashlight. You have a connecting wire from the bottom of one up to a light bulb, and then the other end of the light bulb is connected to the positive terminal of the battery, and you get light, right? So you have a flashlight. And the setup on the right would also work. It's just that they're connected a little differently, and it works a little bit differently. So just what is current? Well, current, and we're going to give current the letter I, is, we said it's charge, right? It's the movement of charge. Well, the way we define current is it is the change in charge over a period of time. Okay, so it's how much charge travels by a certain point in a certain amount of time. So if I had a wire here, all right, I'll try to draw it like I had the one up above, and I were able, say I had all these negative charges in here, and I was able to open a window into my wire. What the current would be if I could count the number of electrons that pass through my window in a given period of time, I could determine what the current was in that particular time. So for example, if I had this window and I was able to make these observations and I recorded that in a particular time of, let's see, we'll make it 10 seconds. All right, so a 10-second window, if you will. I observed 3 times 10 to the negative second electrons. I'm sorry, coulombs of charge. Okay, what would my current be? Well, my current I would be 3 times 10 to the minus 2 coulombs divided by 10 seconds, all right? And my current, therefore, would be, I would equal 3 times 10 to the minus 3 amperes. Okay? Current is measured in units of something called amperes after a scientist from the 17 and 1800s. Okay? So this is what current is. So current is given the letter I, and it's measured in amperes or amps for short. I think most of us have probably heard about amps. We have 20 amp circuits in our house or 15 amp circuits in our house. So we've probably all heard of the ampere before. Okay, so current flows in a circuit. All right, electrons flow from one side of our voltage source to the other side. Okay, so if we look over here on the right, we have the flow of electrons. All right, in this depiction over here, we have the flow of electrons from a battery, all right, through a light bulb to the other side of the battery. And you'll notice that in this diagram, I've just drawn a picture that goes counterclockwise, and that's the direction of the electron flow. All right, that's the actual direction that the current flows in. But when we think about, or we analyze circuits, which we're going to get to in a second, we use what's called conventional current flow. And conventional current flow, instead of going from the negative terminal to the positive, goes from the positive terminal to the negative. Does it change anything? No. It's just a convention. It's the method with which we use to analyze circuits, and we call it positive current flow or conventional current flow, and it flows from the positive part of the battery or voltage source to the negative side of the battery or voltage source. Okay, and so that's conventional current flow. And so if we look at this circuit to the right, or the circuits for the batteries up here, what do we have in this circuit that actually makes up a circuit? Well, we have a source of energy, right? And this source of energy or power, right, is given the symbol that looks like this, okay? And this is the symbol for a battery, okay, without the circle. You won't generally see the circle in there, right? A long line and a short line. The long line is the positive side of the battery. The short line is the negative side of the battery. So in a circuit, we will always have some power source. We're also going to have, so we're going to have a power source. We are also going to have something to connect our power source to whatever device is going to be in our circuit, right? And so generally we're going to use wires. Sometimes in the classes that I teach, we use what we call snap circuit parts. They're very much like wires, except they don't bend. So we have a power source. We're going to have wires or something like wires. And we're also going to have some kind of a device. Okay, so a device or component in our circuit, because otherwise our circuit would be rather boring and meaningless if the electrons flowing through our circuit didn't actually do something for us. In this case, right, the electrons, the energy of the electrons is used to light a light. If we have a toaster plugged in, it's to make toast, right? We get heat out of that. And we could go on and on and on with a million different types of devices, but we're always going to have a power source, we're always going to have some kind of wires, and we're always going to have some kind of device, at least one device. All right, in many instances, we have many devices in our circuits. Okay, so a circuit is made up of at least those three things. One of the properties of a device, all right, in our circuit is that it's going to typically resist the flow of electrons. Our wires, especially as we do circuit analysis, we're going to consider our wires to be perfect wires, and so they are not going to have any resistance in them unless we're doing a lab and we're trying to actually measure the resistance of a wire, or we're actually doing something like that. We're going to consider our wires to be perfect wires. However, our devices are not perfect in the sense of resistance, and they're going to resist this flow of electrons around the circuit. Okay, and so what does resistance do? It simply resists, or it slows down the flow of electrons, therefore it slows down the flow of current. In a circuit like the one I'm going to redraw this over here. We have our battery. We have a device, right? Positive and negative parts of the battery. This is our device over here, and I have given it a slightly different symbol. This symbol over here is the symbol for resistance, right? It's just a squiggly line. In this device here, what do we have? Well, we have a power, in this circuit we have a power source which gives us voltage. We have electrons that are going to flow in the conventional sense there, and so we have a current I, and we have this device here which has a resistance R. And from a physics sense, these are the three variables that we're going to use to analyze circuits. So if we look at, again, our wire, and we've got all these electrons in our wire, right? If I set up an electric field, these electrons are going to flow to the left towards the positive part of the wire, or the positive part of the electric field. Okay. The stronger our electric field, the faster our electrons are going to flow. What makes an electric field? Well, we have a voltage. We have this relationship between voltage and electric field. The stronger the voltage, the stronger the electric field. If the electric field is stronger, the electrons are going to move more quickly. And so we have a relationship. The voltage in a circuit is proportional to the current flow in that circuit. Okay, the greater the voltage, the greater the current flow. The less the voltage, the less the current flow. And so what actually determines how much current is going to flow in our circuit? Well, the amount of resistance in our circuit. Well, in this circuit up here, we have one resistor, or one device that has resistance. We have one voltage source, and we have a wire or wires that are connecting those. And so we have a new law in play here, and it is called Ohm's law. And Ohm's law goes like this. The voltage in any part of a circuit, all right, and it can be the circuit at large, the whole thing, or it can be one small part of the circuit, is equal to the current in that portion of the circuit times the resistance of that portion of the circuit. And the beauty of Ohm's law is it can be used for very small parts of the circuit, or it can be used for the entire circuit. Okay? And we'll use basically three different flavors of this. This equation, this Ohm's law, can be rearranged three different ways, which are all very useful. We have V equals IR, right? That's if we want to know the voltage. If I want to know the current, I is equal to what? I is equal to V over R. And if I want to know the resistance, R is equal to V over I, right? We're going to use this equation a lot, okay? Over on the right-hand side, we see yet another set of relationships. The relationship on the top is for a resistance that obeys Ohm's law. Not all materials, not all resistances obey Ohm's law. The ones that we're going to study in this chapter will obey Ohm's law, okay? And so there's a linear relationship between the voltage and the current. As the voltage increases, right, the resistance stays the same. It does not change, okay? On the bottom, we have a different case, all right? There's not a linear relationship, right, between the voltage, current, and resistance, all right? This is the case in something devices called semiconductors, diodes, transistors, and some other types of devices. LEDs, right, do not obey Ohm's law, okay? So not all devices obey Ohm's law, but the ones that we'll be dealing with do obey Ohm's law. Okay, so speaking of resistance, okay, if I wanted to physically build a resistor or resistance is really a property of the type of material that we're talking about, okay? So resistance is equal to the resistivity of some material, right, times the length of that material divided by the area of the material, okay? So the cross-sectional area, the wider, the bigger the cross-sectional area, the more space there is, if you will, for electrons to move around. The longer the material, the longer it's going to take from an electron to get from one side to the other side, right? And the rho here is the resistivity, okay? So if we're trying to figure out the resistance of a material, and we have its resistivity value, the length, and the area, we can figure out its resistance. Another thing about resistors is that they tend to be, they react towards temperature, or to temperature, okay? And so the resistance of a particular resistor is equal to its resistance at some known temperature times 1 plus alpha, and alpha would be for this type of a material, whatever the material is, how it reacts to temperature, okay? So again, this is a standard equation here. The resistance of any material is equal to its resistance at a base temperature, right? That would be the 0 there, right? And this would be the temperature over here, times some factor that allows us to determine what a new resistance would be at a different temperature. As temperatures cool, right, the resistance goes down. As temperatures rise, typically the resistance goes up, okay? The last thing we want to talk about here is power. Okay. In Newton's laws, we talked about power and where power comes from. Energy, power is energy over a given period of time. Okay. Well, we know that energy is Q times V, right? In an electrical sense, right? The amount of charge times the voltage. Right? If we divide that by time, what do we get? Well, Q divided by T, we found way up here, is current. Right? The change in charge divided by time is current. And so, Q divided by T is current, and so power is equal to I times V. The current running in a circuit times the voltage in that circuit. Okay? Well, we also have good old Ohm's law here. V equals IR. And so there's more than one way to get the power in a circuit. If we replace V, right, with its equivalent from Ohm's law, we have IR, we get power is also equal to I squared R. By the same token, if we replace the I up here, the I up here instead of the V, we get power is equal to V squared divided by R. So all three of these are ways to determine the power that is being used up in a circuit. Okay. So let's do a little example here. Let's say I want to know the amount of charge Q that is flowing in a circuit where the current I equals 2 amps. Okay, and the current is flowing for a time period of 8 seconds. I would like to know how much charge flowed during that time. Well, I've got the equation I is equal to the change in charge divided by time, right? And so our current here is 2 amps. So 2 amps is equal to Q divided by 8 seconds. And so if we multiply the 2 amps times the 8 seconds, what we have is 16 coulombs of charge, right? Which is a lot of charge, okay? So 2 amps is a pretty hefty current. All right, well, let's say by the same token, whoops, we want to use Ohm's law here, and I have a circuit, and this is my circuit. Here's my battery over here with a voltage, say, equal to 9 volts. And I have a resistance, and up to this point I have not told you the units of resistance. Well, the units of resistance are the ohm, after George Ohm, and it's this symbol over here. And let's say our resistance is 18 ohms. And I would like to know the current I that's flowing through our circuit. Well, using Ohm's law, V is equal to IR, or rearranging, we have I is equal to V divided by R. Right? Our current, therefore, is going to be V, 9 volts, divided by 18 ohms equals 0.5 amps. So 0.5 amps would be flowing in my circuit. And this would be the total current for the circuit, because my battery voltage is my total voltage. I only have one resistor, right? So that's my total resistance, so that my total current would be 0.5 amps. I can find the resistance in a circuit the same way. Let's say I have another circuit over here. I've got a resistor there. I'll use the same 9-volt battery. And let's say now that I've got 2 amps of current flowing in my circuit. I would like to know the resistance R of that resistor. Well, again, I'm going to use Ohm's law, but now I want to solve for R. Well, R is going to equal V divided by I, which is going to equal the voltage, 9 volts, divided by 2 amps, which is going to be 4.5 ohms. So that would be the resistance of my circuit. Well, that's it for Ohm's law. In the next lesson that we're going to be doing, we're going to be talking more about series circuits. This is a very basic series circuit, okay? And we'll talk about what makes up a series circuit, how to solve series circuits, how to determine the voltage across different resistances in series circuits. So we'll be covering that in the next lesson. Hope that helped, and we'll see you next time.